And how can we do that? So just recall that like this one block of the a block of things here is called the clause, right? So this is what we call clause, and this is what we call literal, right? So let's construct like a graph, right? So basically the our compilation target is a graph because what's on our hand is a solver for the independent set, right? So we want to feed that to an independent set solver. Um, so in order to construct this graph, so that we are going to construct a lot of little triangles, right? So you sort of see the patterns here, right? So the number of triangles here is corresponds to the number of clauses here, right? So there are exactly three clauses here, right? Clause 1, clause 2, clause 3, right? So we're constructing three little triangles. This corresponds to the clause 1, and this corresponds to the clause 2, and this corresponds to the clause 3, right? This is the first thing. And the second thing is that we are just going to give names to the give names to each of the triangles, right? So I have three little things here, right? So intuitively that maps to three literals, right? So because the x1 bar, x2, and x3 all appears in the first clause, I'm going to name one of them to be x1 bar, second one will be x2, third one will be x3. Right. Similarly, right. So if I just examine the third one, you can sort of see that I'm exactly doing the same thing, right? So x1 bar over here, x2 over here, x4 over here, right? So this is how we construct all the triangles so far, right? So now let's also try a little bit of drawing, right? So far we managed to explain that there are triangles. Each triangle corresponds with to each a clause, right? So we still haven't explained this crossing edges, right? But these crossing edges are also pretty straightforward, right? So if I look at my x1 bar, so I'm going to look for all other x1 and then add an edge, right? So x1 bar and x1 has to add an edge. x2 bar and x2 has to add an edge, right? So and that's the reason that we come up with everything here, right? So there are only two types of edges. Let me just repeat, right? The first type of edges, and I color this multiple times. The first type of edges are really just triangles. You just have to build all these triangles no matter what, right? So within each triangle, right? So the literals are the labels of the nodes, right? So and the second type of edges are really the edges that are connecting between two different triangles, right? So the edges are added only for the two literals that are opposite to each other, right? That is x2 bar connects to x2 and x1 bar connects to x1, right? So whenever you see these patterns, xi and xi bar, you need to make a link over here, right? So now that's basically the entire reduction, right? So what we are going to do next is really just that to really build this graph. And after we build this graph, I feed that into the independent set solver. And when I get an output of the independent set solver, then I can sort of tell whether there exists any feasible solutions out of this for this conjunctive normal form, right? So now basically this is the lemma we have to prove, right? So if phi is satisfiable basically means that there exists a way to assign x1 up to xn such that the phi evaluates to true if and only if there exists an independent set of size k. K is the number of clauses, right? K is really just the number of clauses, right? So for this example, right? So in order to determine whether this phi emits any feasible solution, I just need to look at the output of the independent set solver, right? Let's like just a little bit like hand waving. Let's assume that we are able to find the exact maximum independent set. And if the maximum independent set it's k, then I say that I'm able to I'm able to find a set of assignments for x1 up to xn such that phi evaluates to 1. Otherwise, I say that the phi never evaluates to 1. Right. So now let's just really make a number of observations. the first observation is that the first question is that, right, this observation is really just helping you to understand a bit more of the structure of the graph we constructed here, right? So is it possible to find the independent set of size k plus 1? Right? Can we find any independent set that's larger, whose size is larger than k plus 1, right? So again, k is really just the number of clauses here, right? So the k is the number of clauses, right? So think about that, right? So it may not be that non-trivial, so it's after I tell you the result, right? So in case, like, just imagine in case we are able to find an independent set of size k plus 1, right? But there are only k triangles, right? So at least one triangle will consist of two nodes, right? This is really just the pigeonhole principle. But on the other hand, within each triangle, for any two nodes, there's an edge, right? So this is simply impossible, right? This is impossible, right? Because each triangle can contribute at most one node, right? So let me just repeat the argument. In case you imagine there exists an independent set of size k plus 1, and we want to be able to show there are some sort of contradictions, right? Our observation is that if I count the number of triangles is exactly k. But I have k plus 1 elements in the independent sets. By using the pigeonhole principle, there will exist one triangle that consists of two nodes in the independent sets. But on the other hand, if two nodes fall into the same triangle, they must be connected, right? Which contradict to the definition of independent set, right? Just recall that in the definition of independent set, if I pick out any arbitrary two nodes in the sets, they should not be connected, right? So basically, the answer here is no, it's not possible. Right. So now that basically means that the maximum possible independent set we can hope for is really just exactly k, right? And if we find an independent set of size k, then we can claim that the SAT problem is solvable. Otherwise, it's not solvable, right? Right. So now we do need to, so again, like after we get a bit of intuition, we need to go back to this proof, right? So again, let's just repeat, like 5 is unsatisfiable if and only if G contains an independent set of k plus of size k, and then it's never possible. So our observation just now is that it's never possible to find any independent set of size k plus 1 if we build a graph in this way, in the way that's highlighted here, right? So let's prove first the direction, right? So if we can find that S an independent set of size k, then I'm able to find a feasible solution. Find a feasible solution of the phi, right? So this is the direction we are looking into, right? This is what this slide is talking about, right? So so the first statement says that S must contain exactly one node in each triangle, right? So because as that's the same as the argument we built there, right? So in case there exists a triangle, right? Just imagine there are two cases, right? In case there exists a triangle that consists of more than one node, right? So they cannot, these two nodes cannot be in the independent set. On the other hand, if within a triangle there are no nodes that are selected to be part of the independent set, that means for the rest of triangle there will be one triangle that consists of two nodes, right? So let me just elaborate this argument a little bit, right? So it's the same argument, but let me just be slow a little bit, right? So so now I say that I have 5 triangles, right? And now this is k equal to 5, right? So now S is a set of size 5, right? And we also know that S is an independent set, right? So when S is an independent set, each triangle can contain at most one node, right? So this would probably be a legitimate S, right? So it can contain at most one node. But here, the theorem is claiming that it contains exactly one node, right? So there's a question on that. Is it possible that there's a triangle that contains no node that's in S? Is it possible, right? So the solid dots here, like I'm using that to refer to element in S, right? As it's a set of size 5, right? So we know that for any triangle, it's impossible to have two nodes that are in S because of the independent set assumption. But is it possible to have this kind of triangles? And it turns out that it's impossible, because if I have this kind of triangle, that basically means that for other triangles, there will be at least one that consists of two elements that are in S. Otherwise, it doesn't sum up, right? So if I don't compensate, if I don't add one more a solid load in any of the triangles, if I count everything here, right? So there are only 4 elements in S, but the size of S is exactly the same as the size of the number of clauses, but it's not. So here it's not 5, right? So this is really cannot be S, right? So that means that for S, right? For S, the F that is an independent set of size k, S must contain exactly one node in each triangle, right? This is the reason the second statement works. And now let's move forward, right? So this is this statement. So let's imagine that let's say that this is our independent set, right? Can I? Right. Let's say this is my independent set. Right. This is independent set of size 3. Right. And now I want to use this independent set to construct an assignment for x1, x2 to xn. Right. So the way to construct the all these variables are pretty straightforward, right? So when I see x1 bar, right? So now this one is now this one is x1 bar, right? So basically I just want to set x1 bar to be 1 or to be true. That means that let me just change that. That means that I want to set x1 to be 0, right? Similarly, I want to set x3 to be 1 and x2 to be 1, right? So eventually my solution will be x1 equal to 0, x2 equal to 1, x3 equal to 1. It's very intuitive, right? When you select a node in the independent set, I just set the corresponding literal to be 1, right? So is it possible that, right? Another question here is that, is it possible that somehow I set the x1 to be 2 different values? So is it so now my question is like that, right? So in general, I have a lot of triangles, right? So is it possible that there's an x1 here, there's another x1 bar here. Is it possible that I'm set x1 to be equal to 1 here, x1 bar here, and then set x1 bar to be 1 again here, right? So this would be a trouble case, right? So if I use the rule we mentioned just now to set all the variables, we want to check that it's whether we are going to get into trouble in the sense that, well, maybe the independent set consists of x1 over here and x1 over bar over here, like these are the two elements that are in part of the independent set. If this could be true, then we have to set x1 to be 1 for this triangle, but then we have to set x1 bar to be 1 again for this triangle, right? So I'm setting x1 to be both 0 and 1, like that I get into trouble, right? This is a problematic case. But it turns out that because of our rules of building these cross edges, there will be an edge that's connecting x1 and x1 bar. That means that if x1 is in the independent set, then x1 bar won't be in the independent set, and vice versa. So it's never possible that we get into this trouble that x1 needs to be set to be both 1 and 0. That's the magical part of the entire reduction, right? So we are indeed able to use this rule to set to set all the literal to be true, right? Right. So after we set this one all these literals in this manner, then basically that means that for each of the triangle, right, at least there's one clause that's activated that's set to be true, right? So that basically means that all the clauses in phi are satisfied, right? Let me just repeat what I'm talking about, right? So we start with a lot of triangles, right? Right, and the independent set basically says that each node, each triangle will have a node that's in the independent set if my independent set is size exactly k, right? And then I want to set up the assignment to make sure, so each node is correspond to a literal, right? We just want to make sure each literal is a set to be 1. Right, everything is set to be 1, and this is possible because as I mentioned, I'm not going to get into trouble to set both variable, both the same variable to be both 1 and 0, right? On the other hand, like if you look at each of the clause, right, at least one literal is set to be true for each of the clause, right? So that means at the end of the day, all the clauses are true. That eventually the phi is also going to be true, right? So this is one direction. If there's an independent set of size k, then I'm able to find a solution so that the phi evaluates to true. Now let's move to the other side of the solution, the problem. Sorry, I skipped the slides, right? The other side is actually the previous slides, right? So now, because let me just repeat what I'm doing here, right? So I want to be able to show that after we do the induction in this manner, right? And then phi is satisfiable if and only if the graph we produced has an independent set of exactly k. K is the number of clauses, right? We proved that one direction, right? When that means that if there's an independent set of size k, I'm able to find a satisfiable solution, right? And this direction basically asks you that if there's a satisfiable solution, I'm able to find an independent set of size k. Right, this is the other side of the problem, right? How can we do that? This is also pretty straightforward, right? So we start with an arbitrary satisfying assignment for phi, right? So basically this assignment could be x1 equal to 1, 0, x2 equal to 1, x3 equal to 1, and so on and so forth, right? So now we can select one true literal for each clause and triangle, right? So what does that mean? Let me just go back to this graph and try to examine what does that mean here, right? So let's examine this. And in fact, we shouldn't examine the graph first. We should examine the clause first, right? So because this is a feasible assignment, right? So that basically means that within each clause, at least one literal is going to be true. Right, so I have a feasible assignment. The definition of feasible assignment means that for each of the clause, at least one of them is going to be 1, right? So let's really just pictorially draw all the things. Maybe in our example would be x1 equal to 1. This is 1, and this is 1, and this is 1, right? Let's say like these three are 1, right? And if these three are 1, what I'm going to do is very intuitive, right? So I'm just going to color this to be 1. And color this to be 1, not color to be 1. I'm going to select this node in my independent set. Then using the same process, select the x3 in the second triangle in the independent set, and x2 in the third triangle to be in the independent set, right? This would be the independent set we construct, right? Right? Because this is a feasible assignment, right? It's never possible that where we see an edge that's connecting these two nodes, right? Why is that? Because in this feasible assignment, if these two nodes, these two nodes refer to the same variable, then this same variable it cannot be true. Like it's impossible that we have a scenario that looks like that. It's impossible because we only set one x1, right? x1 could be either 1 or 0. If we set x1 to be 1, then the x1 bar will never be activated, right? So if I look at the clause, right, the corresponding x1 bar, right, it will never be 1, right? So we will not select this as our independent set, part of our independent set. And similarly, if x1 is 0, then we will never select x1 to be part of our independent set, right? So this is impossible, right? So after we selected all these nodes, right, all these active nodes that corresponds to the true variable for each of the clause, then basically they form an independent set. And the size of the independent set is exactly k, because for each of the clauses, we managed to pick up at least exactly one element and put this element in the independent set. right? That's also the other direction, right? So if we put together the two direction together, indeed we managed to construct a uh, solver for what, for the SAT problem based on the solver for the independent set, right? So my SAT problem, do some transformation into the graph, a lot of triangles, and feed that to the independent set and output yes or no. If it's yes, then I also output yes. If it's no, then I also output no, right? Yes means that I ask the question that whether the independent set consists of problem consists of consists of exactly k independent an independent set of exactly k, right? Let me just repeat, right? Um so so basically I have an SAT problem. I translate that into a number of triangles and together with some cross edges. I use this graph to feed into the independent set solver and ask the solver to determine whether there exists any independent set whose size is exactly k. If the solver says yes, then I'm going to output yes for the SAT problem we have in our hand, which means that the CST the CSTP problem we are given has a feasible solution. On the other hand, if the independent set solver says no, there doesn't exist any independent set of size exactly k, then I know that it's impossible to set the conjunctive normal form to be 1. Right, so this is how we do the reduction. With the solver for the independent set, we are able to solve the SAT problem, which means that the SAT problem is strictly easier than the independent set problem. Right, so at the end of the day, we sort of have this very giant chain, right? We see it. 3 set is easier than independent set. Independent set is the same as the vertex cover. Vertex cover is easier than the set cover, right? So this is the logic of the entire what we have done so far, right? Next lecture we are going to continue this kind of the reduction exercises, and then we are going to move to P versus NP. Thank you for your time, and talk to you very